Okay, so question is I have given an array and I have to find that index of that element which is just greater than its neighbors, or which means its adjacent elements. So we have to return that index. So what is the things given in the array, let's say there is a size of array given there, and we already have a array uh, for int I is equal to 0 to I less than n I plus plus, and there is a cin of we have 5. Okay, so we have given one array. There's a one test case also, like 1 2 3 1, and we see one thing that there's a index number 2 which is of element 3 which is greater than its left element and this right element. That means the peak is situated at the index number 2. So we have to return the number 2, and at index number 2 there's a element 3. How to go for this? So the very root that comes to, like, that simply comes to my mind is we simply traverse the whole array and like simply check with left adjacent and right adjacent whether if the element is greater than to both of the left and right adjacent elements. That means we have to return that index number. uh, uh, and what are its constant there? So its constant is the n is goes to up to 1000 10 power 3. So yeah, so if during traversing we simply check each element, and that takes some time. Complexity is of n, and the space complexity is of 1. Okay, but we should go for the optimal approach. So one thing we see there, like we have given an array, and in the case of the formation of the peak, let's say there is a peak is forming there. So it is guaranteed that if there is a peak there, so it is guaranteed that there should be some slant or there should be some slope in the, maybe in the left side or in the right side. So uh, what is the advantage of that slope? Since slope is a monotonically increasing or decreasing, so the first data structure or the first intuition for me to use what's the data structure use there, or what's the thing that I should use here. So the only thing that I should apply for the monotonic nature is I can apply binary search there, because to optimize from off n to further maybe of root n or of log n, so only way is possible is if I have to further optimize it to of log n. So I think we can apply binary search, but there is a problem. Since whole array is not non-monotonic, so we can't apply the binary search on whole of array, but we can do one thing there. We can separate our arrays in such segments, and we apply our binary search on some segments. Segment means when whole segment is showing one monotonic nature, either increasing or either decreasing, so we can apply on segment there. So let's say we see one thing there. Let's say we have given 1 2 3 1. Okay, let's say there's a the size is 1 there, and this is 1 comma 2 comma 3 comma 1. Okay, we see one thing. uh, uh, First of all, we have to judge whether our peak is located on which side. Like the basic idea behind the binary search is we have to just eliminate we have to just eliminate or skip which of the part is not in the answer, is not in the answer. So it is either in the left or either in the right, so we just skip the left portion or skip right portion. So simply that approach we can proceed to this question also. So it means what I have to say, let's say I have an element 2 there. Since let's say I have one element, there's a 1 2 3 and 1. So let's say I'm picking one index, let's say I'm picking index number 1, and there's an element 2. So if I have to judge, if it's, we see it is there's a one condition, there's a, what are the possible cases there? Either the peak is on the left side of this, or either a peak is on the right side of this. Okay, so these are the two cases there. So it means, let's say we assume if peak is on the left side of this too, so it is guaranteed that it is less than of its left element, left adjacent element. Like when we form our left slope there, a decreasing slope there, so we think one thing, we see one thing there, if that whatever index I'm taking is less than of its its left adjacent element. So since I've applied binary search there, so what's the random index? I call it as a mid value, and that mid value that decide what of the part I have to use, or what of the part, what part is I have to skip there. Okay, so so simply we initial similar condition for right side. Yeah, but there's a one edge case also there. Let's say what are the thing that yeah, see, let's say we have one array also, that is of length 4, so n is equal to 4, and let's say that array is 1 2 1 and 3. So now what we do in the condition 2, like when we have index at index number 1, see that I want to say that let's say our array is equal to, there's a 1, there's a 2, there's a 1, and there's the 3. Now what we have to do for this index number 1, so so there's a one thing there, so we explicitly check for this condition, if our array of the mid is if in the fall in such category when peak is on the left side and also on the right side, so we simply go to further any of the peak, because it's a given in the question that we have to return any of the index of the peak. So simply let's say we can move, in this case we can move simply maybe left or maybe right, so depending. So that's the remaining case there. So what I'm trying to say, first of all, yeah, one thing also given in the question is there, that we have to assume the corner elements is always greater than its outer elements there. What it means, array of what it means is there, when we have to finding the index element at starting of the index, we don't have to bother about what it's on left, because it's given in the question that the starting of the element is always greater than its boundary, means a of 0 is always greater than a of minus 1. Similar thing at the end of the index, end of the array, a of n minus 7, because I am using n as a array, so a of n minus 1 is always greater than a of n minus a of n. Okay, so we simply use there, and we can also use some edge cases there. Let's say if n is equal to 1, so the only thing remaining is we have to simply return that only the peak element is exist as a array of 0. And now for all of the n greater than 1 cases, we again check for the boundary cases. If a of 0, now we don't have to bother about on the what is on left side of this a of 0, so we simply check for a of 1. If it is, so we return 0. Similarly, if a of let's say we named this array as a v, so this is n minus 1, and simply if it is greater than of a of n minus 2, so we again return n minus 1 there. Okay, now let's say since we check for the starting of the 0 and n minus 1 element, so we starting our array with s equal to 1 and n equal to n minus 2 there. Okay, and our mid is okay. So our traditional template for the binary search is, first of all, find the mid element, this e minus s by 2 plus s there. Why I use e minus s? Because there is maybe condition if it is of 10 power 32 10 power 32, so there is a overflow if E and S are of that power. So we simply due to avoid the overflow we use E minus S by 2 plus S, because this also equivalent to E plus S by 2. Okay, now we check if our A of mid, if it is A of mid plus 1, what I'm thinking is that if our A of mid is greater than A of minus 1, so it is guaranteed that peak is on left. That means our end becomes to mid minus 1. Okay, similarly if A of mid yeah, okay, yeah, if A of mid is less than of, okay, uh, if our A of mid is greater than A of mid minus plus 1, so it means it is on the right side. Similarly if A of mid it is greater than, okay, so what is there, we have to simply go on the right side there. It means there is a peak is on right side. Okay, there's also one case is there. What is the remaining case there? Yeah, first of all we simply check if the condition is if A of mid is greater than A of mid plus 1, and also if of mid is greater than A of mid minus 1, so we simply return mid now. We simply return mid now. And what the remaining case there, the remaining cases when there is minima. So in case we simply move, let's say mid plus 1, or we can move and equal to mid minus 1, it doesn't matter. Okay, so so it is guaranteed that there must be a one peak in the array. So this is very written, but simply since we have to return something in the outer function, so we return there, return minus 1 there. Okay, and okay, this line is goes to it doesn't matter, we can, because the so we can run this condition whether we can get the what is the value is there. Okay, I'm sorry, I initially named it as A. Okay, so all things are remaining. First of all I define the sizes, then I define the vector there, and by I put input I value putting all of the input in this. I have to check whether if is in one size. I think this should be the correct. So I don't know what is the issue here. So if n equal to 1, it is written 0. What's the issue here? Okay, so think okay, this is the mistake there in the int main. I don't have to return this. I have to what is see out there and there, and now return of 0. Similarly it returns 0 minus 1 doesn't vary, doesn't mean anything. Here also we have to see out there 0 and there, and the return of 0. Similarly this line is also here, and here it is printing C of n minus 1. So I think it is correct. 1 2 3 1. So yeah, let's say this, let's check another cases. 1 2 1 and 6 there. It should return 1. Yeah, it can be 6 there. Let's say if it is 1 there, now it should return 1. So yeah, so that means, so this is the most optimal. And see, we simply doesn't apply any of thing. This is simply a binary search code. So it means its time complexity is of log n and its space complexity is of 1. So thank you.